Okay, so here's a project I've been working on for a while. It is an attempt to make an Arduino-based computer. So what I have right here is very reminiscent of early retro computers in the fact that it has a CPU and then a separate display chip connected to a display. I've always liked retro computers, so this was sort of an attempt at building my own. What I specifically designed this for was for expandability. Each Arduino, or at least processing Arduino, is specifically designed so that it holds all its code in RAM, and that a bunch of them can be connected together in order to increase the processing power. Right here, what I've got is this processing Arduino transmits over these serial lines into this display Arduino, and then this display Arduino holds a buffer and RAM, which it then sends out signals all the way to the LCD screen. Oops. And oh gosh, darned it. So this display Arduino sends out logic signals to the LCD screen, and this display specifically, I keep touching it and making it go blank, but this display specifically is designed to interface with Arduino. And since the Arduino already has a tiny amount of RAM, this holds its own RAM and sort of image buffer. But since I wanted to make this like a retro computer, I specifically restricted myself to only send signals from this dude to the LCD screen. So let's really get to the heart of the difference between RAM and ROM. You see, RAM is all the stuff you can easily change, so I described that by having a whiteboard here. ROM is all the data you can't really change very easily, so I have a piece of paper here along with a marker to demonstrate that. Let's really get to the heart of the difference between a microcontroller and a microprocessor. On the left here, I have ROM. This is supposed to represent all the data, which is very difficult to change. On the right, I have RAM, which represents all the data that's easily changeable. Now you see, typically, what these types of devices do is that they run a bootloader from ROM, which lets them tell sort of where to find all the code it's looking for. Now, in a microprocessor, typically what it will do is that it'll look at some ROM, then look at some RAM to search for the program it's running. But with a microcontroller, what it does is that all of its program memory is stored inside ROM, so it's very hard to change. And what computers do is they use microprocessors. Now, microprocessors, the big advantage between microprocessors over microcontrollers is they're very versatile. I mean, the fact that they can run code from RAM means that it's possible to download programs from online, put them inside the RAM, and then run them from there. However, there's a problem with microcontrollers. You see, it can only run from ROM. So it wouldn't be able to necessarily download something from the internet and then just run it, because ROM is really difficult to change. So here's sort of a representation of the code you might find running a microprocessor. So right here, it has the instruction, execute instructions from RAM. And so the microprocessor reads this and then looks over here. Then in RAM, it looks down and sees that z is equal to a plus b. So it adds a plus b and then moves it into variable z. Then here, it says z squared minus 2z equals z. So it would square z, put that in a separate variable, multiply z by 2, put that in a separate variable, subtract the 2, and then it would finally get z. Then it would look at z, get the absolute value of z, and then move that into variable z. But this wouldn't really work on a microcontroller, since a microcontroller, by definition, cannot execute instructions from RAM. Instead, we'd have to take another route. The process in a microcontroller would be much more difficult. It would have to go here, ask, is there a plus in RAM? And if there is a plus, execute this instruction. So if we look at this, if there's a plus, is there a plus? Yes, there's a plus. Then add the two variables. So we add a plus b. Then we go down. If there is an arrow, is there an arrow? Yes, there's an arrow. Okay, then move the result into the variable. Okay, so we want to move the result of a plus b into z. Now we go back into the instructions and look down. Then if there's a square, square the variable. Is there a square? Yes. And then we continue doing that, and eventually we get to the bottom, come back up, and try again. Is there a plus? Is there a square? Is there an arrow? We do this many, many times just to do a single instruction. For this reason, having a microcontroller trying to run things from RAM is much, much slower. So after hearing about how slow interpreted languages are, you're probably wondering how slow my interpreted language is. Well, I did some calculations and figured out that each one of these is roughly comparable to a 6502 running at 200 kilohertz. That might sound like gobbledygook, but the 6502 was the main processor in the Nintendo Entertainment System, and that ran about at 1 megahertz. So that means that this is about 1/5 the speed of a Nintendo Entertainment System. It's fun, but still not very great. Even though it takes about 88 instructions to execute one interpreted command with my system, it's still very simple. All it does is that it stores the data into two arrays. One of the arrays is code, and the other array is variables. The code stores the interpreted instructions, and the variables just store all the numbers. What happens here is that the interpreter comes down and looks right here, that QEC. The QEC tells the interpreter that it's a question and you want to see if the variable equals a constant. So does variable 16 equal 29? Goes down here, checks it out. Nope, it's 22. If this is true, it executes the following command, otherwise it jumps over it. And then it does similar things to that all the way down here, where it starts doing some more complex commands, including a draw command, which I'll get to later. This is the basic instruction set I've come up with. I tried to make it relatively similar to the 6502 instruction set in terms of power. So I have jump and jump relative, a bunch of assignment operators, some super duper relative addition operators, and here this is the majority of the math functions. Typically on this paper, x means a variable, y means a variable, and c means a constant. So here, x minus y, set x equal to variable x minus variable y. And here it's set variable x to equal x minus constant c. And it works a lot like that. I also have a couple branching operators. You're probably wondering why there is only greater than for these two variables. Well, if you really need to compare less than, then you can just switch the order of the operators. Here is all of the parallel bus I/O. So this design uses a parallel bus to communicate in between the Arduinos efficiently. And so a lot of this stuff can either be left up to just me. So I have some pre-made settings in here, and that's why there's like in mode, clear in, print out, all that stuff. That is really intended for when you just don't want to really mess with the parallel bus and just want things to work. But if you really do want to mess with it, there are some more complicated operators here. Lastly, we have the more complicated instructions. These just wait. Wait is measured in milliseconds, so thousandths of a second. And so sometimes you want to wait more than a quarter of a second, so I have double operators here. And here, this is sort of what I call the sub-assemblies, or subroutines or whatever. The whole idea here is that these are complicated instructions that you might want to use, and they're all implemented in the Arduino programming language, which is compiled instead of my assembled language, so these are going to be faster. And right here, finally, I have the pin in, pin out, serial toggle, and these basically allow you to control the individual pins of the Arduino instead of, just relying on the parallel bus. For the graphics system specifically, the graphics Arduino needs to have pin 2 on it set to high in order to transmit data, and that's because it ends up speeding the serial input. And that's pretty much everything for the current instruction set. So let's make a little bit of an example program. Let's try and do the Pong display thing that I was showing earlier. So we know the display is 30 by 40 tiles big, and we also sort of know the behavior we want. We want the ball to move until it hits an edge, then once it hits an edge, we want it to start moving backwards and continue on like that, hitting each edge. So in order to do that, we might try to figure out what exact variables we need. So in order to do this, you would need to know where the walls are, the direction where the ball's going, and also the position of the ball. So we can just put those into memory. We can just say that, okay, let's say variable 16, that is the x position. Variable 17, let's say that's the y position. 18, let's say that's the x direction. And 19, let's say that's the y direction. Also, in order to not make this ball have a trail, we would also have to remember the previous tile it was on, so we know to just black that out and blank it out. So we can set variable 20 to be previous x, and 21 to be previous y. So now that we've figured out the variables we want to store, we have to figure out the logic of how to use them. So for each tick or frame or whatever, we want to figure out whether or not this ball is on an edge. So if the x position of the ball is greater or equal to 29, which would mean if it's right on this edge right here, then we want to make the x direction negative. And then we copy that with the y direction and all the edges of the display. Next, we would probably want to change the x position to reflect the new x direction. But before that, we gotta remember we have previous x and previous y. So we just make previous x equals x position, and previous y equals y position. Then after that, we want to add the x direction to x and the y direction to y. Oh, wait. Don't mind that. So we would say x position equals x position plus x direction, and then same with y. And then once we have this starting part figured out, then we have to get to the actual drawing code. Luckily, we have those advanced functions to help us with this. Now, if you remember what I said earlier, I specifically said that in order for the serial data to be transferred to the display Arduino, one of the pins has to be activated. On the display Arduino, that corresponds to pin 2, but for the Arduino that I'm running this on, it has pin 13 connected to pin 2. So what I would write here is pin 13 equals high, which means this will turn pin 13 on and send a signal to the display Arduino to start the serial communication. Then we just have to draw the previous X, previous Y, and then just some blank tile. And what's important to note here is that all of the arguments in this are variable arguments. So it points to a point in RAM where we have the specific character indicated. Now here, all the code, or all the RAM starts as zeros. So if we just put 0 in here, the variable it points to will already be 0. Then we want to draw the ball. So that would be X position, comma, Y position. And then remember, this last term is the tile, and it also points to a variable. But you'll notice we don't really have any variable specifically set out to be the tile for this. So we'll just go up here and say 22 is the tile we want to change it to. And then in the beginning, we can just slip in an extra instruction. Tile equals 18. The paper keeps moving. We just slip that in there. And then we can just write tile here. And since tile equals 18, it will draw character 18. And then after that, we just want to pull pin 13 low. Turn it off so it knows we're finished sending data. Actually, I forgot one extra step. We gotta update the display. And that's very easy. It's a single instruction, no arguments. It's just labeled update. We put that in there, and then this would run one time, draw the ball once, and then just finish working. So if we want it to loop over and over again, we would include a jump instruction and jump to code position 0, 0. And this is the pseudocode that we would have to use to run it. Now that we have this pseudocode down, we can go ahead and start writing a program in the assembly language. So first of all, remember I stuck this in. And so if we look up here, the assignment operator is 1, 5. So that would mean the first byte is going to be 0x15. And then we put in the variable, which is going to be, now it's going to be 22. 22, then 18 would be the constant. We go down again. See, this is an if statement. Go up here. We have in if x equals c statement. So we see that is 8 and 8b. So the next instruction would be 0x 8b. Then we see we're testing x position. X position is variable 16. So if variable 16 equals 29, then it's going to execute this next instruction. Otherwise, it's going to skip it. And the next instruction is to make the x direction -1. And because of the specific way 8-byte numbers work, -1 is equivalent to 255. So we go up here, we want to make x equals c again. So 0x 15, then that is xter is variable 18, and we want to make 18 equal -1, which we can turn into 255. And then you continue that all the way down. You look here, figure out what instruction you want to do, look up here to find out the hex code for that instruction, and then put the instruction right in here. So once you would convert all of the pseudocode into the assembly code, you'd get a program resembling something like this. It starts out with the code that calculates which direction the ball should bounce, updates the positions, and then draws everything, and then jumps back to the beginning. And all of that should look a little bit like this. As you can see, the ball's bouncing around the LCD screen. Whenever it hits an edge, it bounces backwards and continues going. The programming language I sort of made for this is really versatile in its abilities, especially because of those sort of sub-functions here. They're complicated, but they're interpreted. Sorry, they're not interpreted. They're compiled, which lets the machine run them much quicker. That's pretty much all I wanted to show with this. So, bye.